He said it's pretty good. Kind of non-standard, but let's see here. So section 2.5 is on covariant derivatives. In fact, the remainder of chapter 2 is all about studying the change of vector fields along a curve, right? So the Frenes-Ray equations are a pretty powerful example of how to relate a given triple of vector fields and how they change with respect to another along the curve, right? But this, what we're about to embark on, is sort of a more general discussion, and it starts with a definition, which, if you really start looking at the pieces inside this definition, they're kind of a lot like things we've already done. So here we go. Suppose W is a vector field on R3. And we'll suppose V is an element of the tangent space to P of R3. All right. The covariant derivative of W with respect to V at P, which we denote del sub little v, big W, of P is equal to W of P plus TV prime of 0. And that is an element of TPR3. Moreover, so if V, big V, is an element of the vector fields on R3, and let's say V at P is equal to little v sub P, right, then the assignment P maps to covariant derivative of V sub P W of P defines the covariant derivative of W with respect to the vector field V, which again is a vector field on R3. And we say that the covariant derivative, well, we say that the symbol, this guy right here, is the covariant derivative of W with respect to V. Now, this is, so like last class, I spent like an hour talking about stuff that it may seem like I'm not really testing on precisely, and in some sense that's true, but the reason I did that in part is for you to notice like this equation here. What's he doing? He's using the line to capture the vector V, right? This is the line with direction vector V going through P. And then he's composing the vector field W with that to take the derivative. This is that stuff we were doing in the section before the Frenes-Ray equation, right? We're taking the vector field, we're plugging in the parametric equations for the curve, we're differentiating it, and then we're setting 0 at the end. This is one of those derivatives along a vector, derivatives along the curve, but the curve we're using is the line. So anyway, this is the covariant derivative. Now, I think we should straight away get to, I mean, I have a example where I calculate it. Oh, fine. Let me do my examples. Example 1. What happens if you take the covariant derivative of a constant vector? Right? If you take a constant vector right? And what happens if you evaluate the constant vector at the path A plus, rather P plus TV for any V? Well, nothing happens, right? When you evaluate the constant vector field, you just get the constant vector field again. So what's the derivative of that? It's just 0, right? There's no time change in the components of the parameterization of W. And as such, this gives us that the covariant derivative of V of W is equal to 0 for all V. Because I can do it for any V at a particular point, so I can just as well do it for vector fields, big V, as well. We'll get there. The covariant derivative, I mean, I think we need some more examples of what the covariant derivative is to answer that question. Example 2, and I'm not sure this example is really going to do it, but let's do this example just to gain a little bit more calculational, footing for what the covariant derivative is. This one, I've got W equal to x squared u1 plus y u3. All right, and I want to find the covariant derivative in the v direction, W, at the point, what point do I say? 1, 2, 3. And my little vector v is 2u2 plus u3. All right, so fine. Sort through the definition here. What do we got? We need to calculate W of what? Of 1, 2, 3 plus t times what? I'll go to the other notation, right? Is that okay with you guys? 0, 2, 1, right? This is W of P plus TV, which is, let's see here, so W of what? 1, comma, 2 plus 2t, 3 plus t, right? Now this W, I do x is equal to 1, so I've got u1, and my y is 2 plus 2t, and that goes in the u3 direction. Now I differentiate, and I set time equal to 0, and that's the covariant derivative at 1, 2, 3 in that v direction. Yeah, so let's see here, W prime of P plus TV, as advertised here, is 2u3. So there you go. This is, in fact, the covariant derivative of V of W at the point 1, 2, 3 is 2u3. So the covariant derivative of a vector field is itself another vector, right? The covariant derivative of a vector field at a point in a particular vector direction is itself a vector. What the vector describes is how the given vector field is changing in the direction of the given vector.
So like if it's a circle, it's telling you like how it's going.
Yeah, but I think that the answer is better given by the next theorem, actually. So let me kind of go on to that. I mean, if you're not comfortable with covariant derivative yet, totally acceptable. Like it's not. it's something like taking the directional derivative of each component of the vector field separately. It's something like that. We'll come to a more. I have more to say, but one thing at a time here. So V, W, vector fields on R3, then the covariant derivative of V in the W direction is equal to the sum J equals 1 to 3 of V acting on Wj in the Uj direction. It's probably healthy for us to go through the proof of this at this point. So W prime of P plus TV of 0 is the sum J equals 1 to 3 of dWj at P plus TV, right? This is just like that Y calculation in your homework we were talking about today, Audric, for example.
Yeah.
So that's the definition. We differentiate each component, the jth component, like that. But then I say, okay, well that is really, this is nothing more than, well, it's really V at the point P acting on Wj. Uj. Oh, I mean, that's the, well, that's the theorem. So, I mean, you could also look at this. This is the directional derivative. This is, in fact, the directional derivative of the Wj function in the V direction at P, right? I think that's what I have in the notes also. And I've, now, okay, so there are many nice properties for the covariant derivative. Like we have the covariant derivative of u plus v of w is covariant derivative of u of w plus covariant derivative of v of w. We have that kind of linearity. We have the linearity that if we have u plus w here, we can break that up as well. Right? It's important to notice the distinction. If we have a function times the vector field here, and see, you've already come up across this in your homework, the distinction between a function being here, and it turns out that you can pull the function out, versus, you know, this one, the covariant derivative of v. I can't put a function inside here, but I can put a constant inside, and I can pull a constant out there. So the role that v and w here play, they're not symmetrical, right? It is the covariant derivative of w with respect to v. And the order matters. They're asymmetric in their role. Now, if you, instead of having a c here, you have an f, well, the way that works, there's a product rule. It ends up being v of f in the w direction plus the f times the covariant derivative of v and the w with respect to, covariant derivative of w with respect to v. And then 6, if we have u acting on the dot product of v and w, that is equal to the covariant derivative of v with respect to u, dot product with w, plus v dot product with the covariant derivative of w with respect to u. Like that.
This has a lot of similar properties as the other thing.
Yeah,
Vector space is a tangential.
it is very reminiscent of the rules for derivations. Yeah. So I'll go through the proofs of some of these on the video because I think it's better for me to just point at my notes in the video. It'll be much faster and accomplish about the same. But I think what's good for you to watch me do at the moment is to work out the formula for the covariant derivative. All right? We'd like to see the formula for the covariant derivative. So I just want to get us just kind of our foot in the door of the last part of the chapter here. So past this point in the section, I have a proof of these, and I have a couple of calculations where I actually calculate using that proposition. It's very, very similar to the homework that you were working today for the push forward, but it's different, but it's kind of the same calculus. So here's the thing. If we have a frame, you know, E1, E2, E3. Suppose we have a frame, and I'll just talk about a frame on R3 for the sake of discussion, you know. Then you can write a vector field, right? You can write a vector field how? You could write it as the sum, well, say J equals 1 to 3 of V upper J Uj, right? We could write it that way. Yep. We've worked some with that already, right? But we can also work with expanding the vector field with respect to a non-coordinate frame. In other words, you could also expand it something like this. Then let's use a different letter, F upper J EJ. Now here, E1, E2, and E3, they don't have to be U1, U2, and U3. All right? And generally speaking, E1, E2, and E3 don't have to be constant. Right? Notice that the covariant derivatives of Uj, right, with respect to any V, what are they equal to? Yeah, they're equal to 0 by example 1, right? They're 0. But the covariant derivative with respect to V of Ej is not equal to 0 necessarily, because it could change from point to point. Those derivatives don't have to automatically be 0. All right? So what happens then, if you just, you know, suppose you believe me that these formulas are legitimate for the sake of discussion, and we wanted to calculate the covariant derivative of V, you know. Let's see here. I mean, uno momento. Make sure I got the right. Where'd you go? Get back here. All right, well, very good. Covariant derivative of all right, well, little. Remember I told you earlier, like the hardest thing was when you don't remember what the problem is? This is what I was talking about. All right, so, oh yeah. So we have, we have right here the formula for the covariant derivative done in the Cartesian frame. What I'm trying to get at here is what would the similar formula look like for the non-Cartesian frame? Right? Like, what if I try to do that, but not for, you know, so let's let W equal to the sum, you know, I, J, whatever you want. I equals 1 to 3. I'll use G, Gj, Ej. All right? I want to try to work out what's the covariant derivative of V, of W with respect to V, and I'm going to try to... Oh, okay, do J? I'll do this I. Yeah, I. I want to have one over I and the other over J so I don't get them confused, you know? Okay, so explicitly then, this is covariant derivative. V is the sum J equals 1 to 3 of F upper J, E lower J, right? That acts on the sum I equals 1 to 3 of G upper I, E lower I. No, the one is of V and the other is of W.
Oh.
See? That's why I need two sets of coefficient functions, one with respect to, one for the V vector field, the other one for the W vector field. And, okay, so if we believe the properties of the covariant derivative, right, then we can pull the sum out. We can pull both of the summations out, right? It's additive in both slots. And we're allowed to pull out functions from the V, from the V entry, right? So we can pull out the sum over I and J, and we've got our F upper J out here, right? But then we're looking at the covariant derivative in the EJ direction of, well, G upper I, E upper I. I can't pull that GI out because it's possibly a function. It doesn't have to be a constant, right? We're looking at vector fields. And then we do the product rule. So this is the sum, I and J, Fj, and then I have to do what? How's this work? See here? So I'm supposed to do what? I'm supposed to do yeah, I'm supposed to do V of F, right? But here V is Ej, so I do Ej of Gi, right? Times Ei. And then plus plus Gi, the covariant derivative of Ej Ei. This might actually not be in the notes. I just thought it would be interesting to try to work out. I'm not sure quite what to make of that Ej G upper I term right offhand. Now the other one over here, this stuff, all right, that actually, we define that. There's a definition that's made for that term. All right, so here's the definition. covariant derivative oh, well, stink. Oh, rats. I chose poorly. Oh, okay, I'm stupid. Look, we can put these guys back together. This is what I wasn't seeing a second ago. You put these guys back together, what do you got? That's, but that is, that's V again. So what this is the sum over I. This is actually V acting on G upper I, EI. That's that first term. And then you got over here plus the sum over I and J of F upper J, G upper I, covariant derivative of EJ, AI. That's progress. And because the first term, see this? This piece right here is completely simpatico with this whole proposition, right?
Why did you take the I and J out of the summation what you said with blue?
Why did I what?
You took you didn't put I and J.
I didn't put I and J. Oh, yes, because the sum over J collapses into this V.
Oh, okay.
That's V. Now the other one, still there. And so, long story short, omega ij of V is defined to be the covariant derivative V EI dot EJ at the point P. So what this is saying is that
You can set that term in 4, so no omega.
yeah, I guess I should, maybe what I should do here is what I have,
Well, GI is not at the point.
I have this term right here.
Yeah.
I can rewrite that as the sum over, let's bring the F back inside. I made a poor choice in factoring the F out is basically the problem here. If you look at page 48, there's like a slightly better way of doing it there. I did prepare for class, by the way. Anyway, yeah. What I'm trying to say here is bring the F inside, bring the sum over I inside, change this to a V. And you got sum over I of G upper I, covariant derivative in the V direction of EI. Okay? That is literally that term. And the reason I would write that is because then I can convert this in terms of the so-called connection coefficients, which are right here. See, this is exactly the sum over I of G upper I omega. Oh, goodness gracious. Stank. Oh. All right, so like everything else we've been doing today, this is a vector, right? And I can expand it in terms of the frame. So this is the sum over I, GI, sum over K, all right? Sum over K of the covariant derivative in the v direction of EI dot EK, EK. So using that expansion, that frame expansion with dot products again. It's like the 20th time today we've done this. But now with respect to an abstract frame. But this right here is omega I think K acting on V. Right? And so this part of the formula just becomes the sum over I and K of G upper I omega IK EK. So anyway, what I was trying to get to today and is just to show you that when we don't use the U1, U2, U3 basis, this happens instead. We get the covariant derivative of V of W is actually equal to the sum J equals 1 to 3 of V of, well, let's see here to start with, GJ, right? And then EJ, right? Plus the sum, and you can combine these if you want, but here's the sum over I and K of G upper I omega IK, and I forgot my of V here, right? It's supposed to be omega IK of V. Omega IK of V EK. And that is the formula for the covariant derivative when we don't use the Cartesian frame. When we use a possibly non-constant frame, we get this interesting new piece for the covariant derivative. These connection coefficients are something new. And what they are, basically, they're telling you how the ith basis element is rotating into the jth basis element in the v direction. So these connection coefficients are telling us about how the given frame is rotating from point to point. I mean, these connection coefficients are very much analogous to what we did with the Furness-Ray equations today. The coefficients in the Furness-Ray equation are, in fact, specific examples of connection coefficients. It's one of the things that is an example in my notes, or maybe it's a homework problem of yours, I forget. But anyway, there is much more to say, Audric, and some of the questions you've raised will be answered in the video. So the examples that are left in the covariant derivative section have to do with what it means. Like the covariant derivative of V in the V direction is 0, for example.
For the omega of IK, why did we,
Yeah, like
that variant of EI dot EK is V.
yeah.
Yeah, you can change that to the omega IK to the V.
But it turns out, though, here's the interesting thing, is as we study these kinds of things more, there's a way to do all of this with wedge products that ends up being particularly elegant. It's natural to think about the connection form as a matrix of one forms. And so I'll show you that in the video and show you how it works and stuff. But anyway, which is kind of surprising from this point. Like where we got to right now, the fact that the wedge product has anything to do with the connection forms is not at all apparent. Like that's just a completely, like what? But yeah.
So you basically derive it from the four form, or you just combine the four form?
Well, this right here, how do you, what's your question?
Like, so you said you combine the one forms? What would that give you, like a four form?
Well, we'll see. We'll see. But anyway, I'm going to stop here for now because I think it's a good place to stop. Is that okay with you guys?